Okay, so first section we'll look at in Chapter 5 is 5.1. It's on exponential functions. And I just want to start by comparing those two expressions I wrote. Okay, in each case, you have a base and an exponent. But if you look carefully at the exponent, depending on what it is, that can tell you whether or not you have an exponential function. So between the two that I have here, x squared and 2 to the x, does anybody know which one of those is the exponential? Priya? 2 to the x. Yep. Okay, so in the one on the left, okay, x squared, the base is a variable, and the exponent is a number. Okay, that's just a polynomial. Okay, x squared. It'd be a parabola if you graphed it. Now, if you put a variable in the exponent and make the base a number, that's when you get an exponential. And we'll draw some of these out, but we'll start to see that exponentials are one of the fastest growing functions that you have. Okay, they curve up very, very quickly, or down very quickly. Okay, so as I said before, the one on the left, that's an example of a polynomial. Okay, so polynomial, you have the variable in the base, and the exponent has to be a non-negative integer. So for example, x to the 1.4 power, that's not a polynomial. Okay, your exponent has to be non-negative, and it can't be a fraction or decimal.
You can go up.
All right, and now when you switch it, okay, and you put the variable in the exponent, that's when you get an exponential function. There is one important thing that we have to be careful with, and that's the base of an exponential. Okay, the base of an exponential has to be a positive real number. And the only thing it can't be is 1. I'll show you what happens if it's a negative number. When the base is a negative number, it's very, very strange what happens. But what would happen if you had an exponential and you wrote the base as 1? Like you said, all right, I'm going to see if this is an exponential function. Y equals 1 to the x.
You'd always get 1.
You'd always get 1. Okay, it doesn't matter how many times you multiply 1 by itself. It's never going to grow. It's never going to shrink. It's just going to stay 1 all the time. All right, let's take a look at what happens if you don't have a positive base. Okay, let's say I had this. Okay, so this is not an exponential function. Let's do y equals -2 to the x. Let's just start to think about some of the values we would get if you try to even figure that out. Okay. So I'm going to try to pick some we can do in our head, maybe some we need the calculator for. What would you get if x is 0?
1.
1. Anything to the 0 power is 1, so that's fine. Let's do 1. What's -2 to the first power? That's -2. Okay, so that's fine. Now, let's do 2. So it's 4.
So it'd be like a wave, right? It'd be like...
Well, let's do 3 and see what happens. What's -2 cubed? -8. So look what's happening to the y values. This isn't even the weird part. Yeah, every other integer is positive, negative, positive, negative. Now let's try a decimal. Let's try 1/2. if I raise negative 2 to the 1/2 power, what does that mean?
Square root.
I'm trying to take the square root of negative 2. And what's the square root of negative 2?
Imaginary.
That's imaginary. So that one we can't even figure out. Okay? So now there's a value that doesn't even exist. But now let me do something like this. Let me raise it to the 1/3 power. Okay. What does that mean if I take negative 2 and I try to raise it to the 1/3 power? Right. It's like I'm trying to take the cube root. And now, can you take the cube root of a negative?
Yes.
Yes. And you get some number. It's negative 1.26. So what ends up happening here is you can raise it to fractional powers as long as the denominator is an odd number. So you could raise it, for example, to the 1/5 power or 2/5 power. Okay, you could do things like that. But if you try to raise it to a denominator with an even, where the denominator is even, it's going to come out imaginary. So now we have all kinds of weird things. So like, let's say you tried to do this. Negative 2 to the 1.6. Could I do it? I don't know. Let me write it as a fraction. 16/10 is 1.6. And that would reduce to, what, 8/5. So that one I don't think I would be able to do because it's an odd denominator. And I can't take, oh no, odd, I'm sorry, you can do. You can take odd roots of negatives. Now, if it reduced to something that wasn't an odd, then we wouldn't be able to do it. So the point is, when you have a negative base, it's really weird. And if you try to graph it, you won't even see anything.
Yeah, like, just try to graph it, there's nothing.
Yeah, you can't graph negative 2 to the x. You can generate a table, and you can look at it if you want. And you'll get the same table we came up with. 0, you get 1. 1, you get negative 2. 3. But then try 0.5. Okay, there's an error, you can't do it. 0.6. Now 0.6 you can do because that as a fraction is 3/5. That's an odd denominator. 0.8. I can do that. That's 4/5. Okay. 0.9. I can't do. So it's very, very weird what numbers you can and can't do. So you might, it doesn't look like we can do any of those. But then we get to 1 and we can do 1. So, all right. So we're not going to study what happens when it's a negative base. But did you have a question, Luke?
Oh, I was going to wonder what it looked like when it was graphed.
Yeah, you won't even see anything. No, won't even show it. Even if you try to trace, see, most of the values you can't even trace to. If you type values in, it'll do it and it'll show it, but that's like an infinitely small point. That's why you can't see it. Even if you zoom in, you
So we're
probably won't
smarter
see it.
than the computer still.
Yes,
Okay. Until Skynet gets created.
right,
And then we're all dead.
and we're gone.
I'll be John Connor, Mr. Hager, don't worry. I'll save the human race.
Thank you. All right, so
Mr. Hager's the Terminator.
anything here that's of this form, okay, a to the x, that's an exponential function. Now the domain of an exponential function, let's look at a real one. 2 to the x. Okay, the domain is how far left and right it goes. How far to the left does it look like it's going? 2 to the x. Yep, it's going to negative infinity on the left. And how about to the right? Yeah. It's going to keep heading to the left and the right forever. So every single exponential function, no matter how you transform it, the domain is always negative infinity to infinity. That never changes. Yep.
Aren't the ones where if it approaches 0, it will approach 0 but never touch it, right? So it'll go up, but it can't hit 0.
Yes, this is a horizontal asymptote in this problem. This will never hit 0. Okay? I don't care how far to the left you go. Okay, if you do -1, you're at a half. -3, you're at roughly 0.1. -5, you're at 0.03. It gets close to 0 very, very quickly, but it will never reach it. Okay? Eventually, it's going to start to write it in scientific notation, so that's 0.0009. But you're right, there is a horizontal asymptote. You never reach 0. Okay, and again, make sure for an exponential, a is a positive real number, and it can't be equal to 1. Okay, so these are all examples of exponential functions. 10 to the x, 4 to the v, pi to the x. Okay, as long as you got a base that's not 1 and it's positive, you're good. These are not exponential functions. Okay, the first one is a cubic polynomial. The second one is a 4th degree polynomial. And the third one is kind of a combination of a rational function, because it's a fraction, and a radical function, because the numerator is a square root. Okay, but none of those are exponential functions. Okay, so any questions on the ones that are or the ones that are not? So what I want to do now is I've already got the one on the left typed in, 2 to the x. I want to graph 3 to the x. Anybody have a guess how 3 to the x is going to be different than 2 to the x? Ian?
Vertical stretch?
So a vertical stretch would be if I did something like this. This is a vertical stretch of 2 to the x by a factor of 4. So you have to multiply by a number in front. It's going to have something to do with how fast it curves. What do you think 3 to the x is going to do? It's going to curve faster, because taking 3 and raising it to a power is always going to be, or usually going to be bigger than taking 2 and raising it to a power. Okay, so let's look at it. Okay, so I got 2 to the x. You don't need parentheses around the 2. 3 to the x. And in general, 3 to the x curves up faster. So the red one is on top of the blue one. But that's not always true. Okay, if you zoom in a little bit, okay, and just kind of investigate what's happening, you zoom in. Okay, the red one is actually below, okay, for certain values of x. Okay, where is the red one below?
Negative, when it's negative.
Yeah, for negative values. Okay, when x is negative, the red one is below, and then when x is positive, the red one goes up above. And they both go through the point 0, 1. Okay, because anything to the 0 power is what number? 1. Okay. So that's all I wanted you to see, is that they cross each other right at this point. 0, 1. All right, so the other thing that we got to deal with is sometimes we have negative exponents. Okay, so back from Algebra 1, we have a way that if you have something with a negative exponent, we can turn it positive. And all you have to do is take your negative exponent with the letter and put it in the bottom of a fraction. Okay, and that makes it positive. Okay, so what if I had something like x to the negative 3? How could I turn that into a positive exponent?
1 over x.
Yeah, 1 over x to the third. Okay, so a lot of times it's helpful to get rid of the negative exponent, just so we don't have to think about negatives. Okay? All right, so let's think about this one. A to the negative x. What number is in front of the x, but it's invisible? Yeah, there's an invisible 1 in front of that x. Okay, So a to the negative x is really this, a to the negative 1 times x. Now, whenever you multiply numbers in an exponent, how does that happen? There's a rule that you multiply two numbers together in the exponent, but when does that rule happen?
The same base.
When you have the same base, you add. So if you had this, that's when you take the 2 and the 3 and you add them together.
You're distributing, so we multiply, right?
So can you give me an example of a...
Like if it was like a to the first in parentheses to the third.
Yeah, when you have something like this. When you have a power to a power, that's when you would end up multiplying them together. So let's rewrite that as a power to a power. It's a to the negative 1 to the x. Okay? That's how you would end up multiplying those two together. Okay? And that's what I have right there. Okay, so now I'm just going to continue with this step. Well, what did we just say a to the negative 1 is? This part.
It's 1 over.
Yeah, we just did that up above. It's 1 over a. Okay, so that's my point. If you have something raised to a negative exponent, all you have to do is take the a and make it 1 over a, and you can make the exponent positive. It's kind of a shortcut, so you don't have to go through all these steps. So let's say you had 3 to the negative x, and I wanted to turn it into something to the positive x. What would I put inside the parentheses? 1 over 3. Okay, so now I won't go through all these steps in the middle. I'll just take this number, 3, flip it, and make the x positive. All right, so that's generally how we want to think about negative exponents. Get rid of them. Okay, don't think about them. Make them positive.
Can you go back?
Mhm. All right, so what I'm going to do is I'm going to graph 2 to the x and 2 to the negative x, and I want to compare them. Somebody tell me how I could rewrite this with a positive exponent?
1 over 2x.
Yep.
Over 2 to the x.
1 over 2 to the x. There's going to be a big difference between 2 to the x and 1/2 to the x. Does everyone have what's on the left?
Hold on.
Does anybody know what the big difference is going to be? Even more than the sharpness of the curve, it's going to be a totally different graph than like 2 to the x and 3 to the x when you graph 1/2 to the x.
Is one going to go down and decay while the other one is going to grow?
Yes, one of them is going to be growth, one of them is going to be decay. Okay, so here's 1/2 to the x. I'll do zoom 6. There's your 2 to the x, that's your growth. And there's your decay. In fact, those two functions are what? They're mirror images of each other. Okay, so that'll help us when we find domain and range. Let's look at the blue one. Okay, that's the 2 to the x. What I'll do is I'll circle that one in blue. And that's the red one. So how far left and right does the blue function go?
Infinitely.
Yeah, we already said the domain is always negative infinity to infinity. And how about the red one?
Infinitely.
Yeah, if you have something that goes negative infinity to infinity and you mirror it, it's still negative infinity to infinity on both. Okay, so the domain is negative infinity to infinity for the blue and for the red. Now let's look at the blue one. Does it go up forever?
Yeah.
Yep. Does it go down forever?
No.
No. It comes down, but it levels off, and it approaches what number? it approaches 0. Does it ever reach it? No. So it'll go from 0 to infinity. And now how about the red one? What's the lowest that the red one goes and the highest?
Is it the same?
It's the same thing. Yep. It's a mirror image, but it's still, the range is still the same. 0 to infinity. Okay, and the reason it'll never hit 0 is because when you take a fraction and raise it to a power, let's say you square it, you're doing half times a half. That's a quarter. Okay, if you cube it, you're doing half of a half of a half. That's 1/8. If you keep taking half of something over and over, do you ever have 0 of it left? No. It'll get smaller and smaller and smaller and smaller, but it never reaches 0. All right, so now what I want to do is look at a function like we just have, 2 to the x. Okay, so this is kind of like the one in blue, but let's try that. That's the one in blue, except I'm generalizing it for any base. It doesn't just have to be 2 to the x or 3 to the x or 12 to the x. It could be any positive real number to the x. All right, so looking at the graph in blue, as x heads towards infinity, what's happening to the y value? And then what's it heading towards? Infinity. Yep. Now, looking at the blue one, trace along it. As x heads towards negative infinity, what does the y value approach?
0.
It approaches 0. Right? So that's for a growth function. We haven't formally given that name yet, but that's what it is. Now let's look at it for a decay function. Let's look at the graph in red. What happens to the graph in red as x heads towards infinity? The y value approaches 0. All right, and now looking at g of x, looking at the red function, what happens as x heads towards negative infinity?
Y approaches infinity.
Y approaches infinity. Okay, so what I'm really showing here is that these are mirror images of each other. Right, they do exactly the opposite thing as you head to the right and you head to the left. Okay, one of them heads towards infinity, the other one heads towards 0. Okay, now the key difference between those two functions is basically whether the base is greater than 1 or between 0 and 1. Okay, if you have a base greater than 1, that's when you get the growth. Okay, take a number in your head like 2 and keep multiplying it by itself. It's going to grow. Right? Take a number between 0 and 1. Okay, take like, sorry, I'll put that back up. Take a number like 0.4. And now keep multiplying 0.4 times itself. It's not growing. It's decaying. Okay, it's going to get smaller and smaller. Okay, so that's the key difference. Greater than 1, you get growth. If your base is between 0 and 1, you get decay. And we'll talk in a little bit about two special kinds of growth and decay. We'll talk about doubling, something doubling over time. And then we'll also talk about half-life, which is a decay. Right, so we can transform functions just like we've done every other function all year. Okay, what I can do is I'll make a table for you or a diagram so you can see all the transformations. Okay, so let's do m raised to the bx plus a, put times c in the front, and plus d on the end. A, B, C, and D each do something to that function. And the letters I used are the order you would do them in. Anybody remember from yesterday what the first transformation you always do is?
You just go up on the second page a little bit.
What's that A going to do? Ian, you think you know?
What? No, I don't know.
No? Nick, can you help him out?
Horizontal shift.
Yeah, that's your horizontal shift. How about B? What's B going to do?
Oh, that's your horizontal stretch.
Yep, it's your horizontal stretch. We'll talk about what happens if B is negative in a second.
Horizontal stretch.
What about C? Priya? Stretch. That's your vertical stretch. Anything that's multiplied is a stretch. Okay, so vertical stretch. Anything that's added or subtracted is a shift. So what's D? That's your vertical shift.
Is it the horizontal ones like what you wouldn't think it is?
Yep, the horizontal ones are always the opposite. So if you were to compare, for example, this one and this one, 2 to the x plus 1 is a shift, let's see, left 1 unit. Okay, this is a shift left 1 unit. If you put a big number in for B, bigger numbers cause the graph to, compress. Small numbers cause it to stretch. Now with the vertical stuff, it's not the opposite. A big number for C stretches it bigger. Small number for C compresses it. Positive number for D shifts up. Negative shifts down. What about if you had a negative for B or C? What would those do? And actually, we did one. We graphed 2 to the x and we graphed 2 to the negative x. They're reflections. Okay? One of them is a reflection over the x. One of them is a reflection over the y. If you make B negative, that's a horizontal reflection. That's over the y-axis. If you make C negative, that's a vertical reflection because it's with the number that does the vertical. And that's a reflection over the x-axis. Okay, I don't think I showed you a reflection over the x-axis. That's the y. If I wanted to make it the x, you go like this. That's putting it in front. The last one I had, the negative was with the x. Now we should have a mirror image over the other axis. And we do. Okay, so any questions on that? All right, so now let's see if we can list out our transformations here. You know what I'll do? I'll put them over here. So let's list all the transformations. Oh yeah. Let's list all the transformations to change this into that. Okay. First of all, how many transformations are happening? 3. Okay. What's the first one?
Vertical shift.
It's a horizontal shift, which I can describe when I say left or right. Or you can say horizontal shift left, but that's a little redundant. So we're going to shift left or right.
Left.
Yep, shift left. I know it's horizontal.
That
1 unit. All right. Second, we are going to shift down, but there's something else we have to do first.
Is it the vertical stretch?
Vertical stretch by a factor of 2. And the third thing?
Shift down 5.
Shift down 5. that's it. So that's, again, another important thing for the test. Make sure you understand what each number in each position would do.
Mr. Hager, you ruined your line though. It used to be nice line.
Oh, yeah, what did I do? Yeah, I messed it up. I can't fix it now. Sorry.
Scroll. You could Oh my god.
Every time I scroll, it's going to mess up. So we're done with that page.
Oh.
Nope, you didn't see it.
No, there it is.
Gave up.
All right, so this function, I just want you to watch me draw it and see if you notice something. So I'm taking 1 plus 1 over x. And actually, you know what? You don't even need the time symbol. You can just put 1.025. And that's perfect to the x. Now, y is my population. What's the minimum amount of people that I could have?
50,000.
Yeah, it's my starting population. Now, I want to know when I'm going to hit 100,000 people. So set your y max a little above that. 110,000.
Now, wouldn't it be easier to put a line at 100,000?
Yep, we're also going to put a line at 100,000. I'm just going to set my time first. Can time be negative? No. It can? Oh. And then the 2.5%, that's the change per year. So right now, we're going to look at data 10 years out. Let's look at data up to 40 years out. Okay, and see if we hit 100,000 people within 40 years. And as John said, put a line in at 100,000. All right, so you can see it. That isn't straight. There is a curve to it. And we're going to hit 100,000 people at about 28.07 years. All right, so within 28 years, the population will double. If it goes up at the same rate every year. Okay.
Where's that one?
What's that?
He said what the horizontal line meant.
Oh, the horizontal line, that's at 100,000 people. And then the blue line is my exponential curve. So I'm just figuring out when my population hits 100,000 people. So it hits 100,000 people at 28.07 years. Now, if it said the population is going up at 2.5% per month, then this 28.07 would represent months, not years. Okay, so I just have to look at the problem to see that. Okay, any question on that one? All right. So be careful whenever you graph about including negatives. Okay, a lot of times negatives don't make sense because it might be negative time, negative money, negative people. Well, there are negative people, but not that kind of negative people. So just be careful about negatives. Okay, the next example of growth I want to look at is a specific kind of growth, and that's doubling. So we're going to finish by looking at a specific kind of growth, doubling, and then a specific kind of decay, halving. Okay, those are opposites of each other. So let's say we start with 100 bacteria, and we double it every hour. How many bacteria do we have at the very beginning? That's like 0 is the initial amount. 100. How about after an hour? 200. Now, what I'm going to do is I want you to focus on the column on the right, because that's going to be a pattern you see. It's 200, which I'm writing as 100 times 2 to the first. 2 having to do with doubling, and 1 having to do with how much time has gone by. How many bacteria after 2 hours? 400. But I'm going to write it as 100 times 2 to the second. Okay. Now after 3 hours, it's going to be 800 But how do you think I could write that one?
100 times 2 to the third.
100 times 2 to the third. And then how about after t hours? 100 times 2 to the t. So the general formula for something doubling is how much did you start with times 2 to the t divided by the length of time to double. So if something's doubling every 1 hour, then this exponent, this denominator, would just be a 1. If something's doubling every 6 hours, then you would have to put in a 6 for length of time to double. So it's initial amount times 2, and then your exponent is t divided by length of time to double. Okay, so this one says we have 100 bacteria, and it's doubling every 1 hour, every hour. I want to know when I hit 350,000 bacteria. Okay, so what's my initial amount? 100 times what comes next? 2 to the t divided by, what is the length of time for the bacteria to double?
An hour.
1 hour. So really, I don't need to divide by 1 in this case. So there's your formula. And how would you figure out when it hits 350,000?
You just set it equal to 350,000.
Yeah, you'd put a line at 350,000, okay, just like we did on this problem. Graph your curve and see where they cross. Okay? Does anyone need me to do the graph of this one? Again, just put a line at 350,000, graph your curve, calculate the intersect. You're going to have to go pretty high, okay, on the y max. I'd go to 400,000. Okay? So it's going to be way, way up. And that's how you do this one. So the only difference is this number is a 2. Okay, what do you think that number would be if you had a bacteria tripling? Yeah, it would be a 3. Okay. Now, what do you think that would be if you had something, let's say the bacteria was getting cut in half every hour? Yeah, it would be a 1/2. Okay, and something like that is called a half-life. So a lot of times they talk about half-life with like radioactive material. Has anyone ever heard of that before? That's why, like when there's like a nuclear reactor that has a problem, some of those waste products can have thousands of years of a half-life. So that means, let's say you created some nuclear energy, and it resulted in, let's make a simple number, 200 tons of radioactive waste. If the half-life was 1,000 years, that means for that, what did I say, 2,000 tons? Or whatever, 200 tons. If the half-life is 1,000 years, that means it's going to take 1,000 years for half of that waste to disappear. So if you had 100, half of it, after 1,000 years, you'd have 50. After another 1,000 years, you'd have 25 tons. After another 1,000 years, 12.5. So every 1,000 years, it gets cut in half. So it gets smaller and smaller. It takes a long time. But it'll never reach what?
0.
It'll never reach 0. There's always a little bit left. Okay, so this is a substance that decays very quickly. Okay, and some elements, like in chemistry, you probably studied different elements, like they can create them in a lab. They're not always naturally occurring, but they have such a short half-life that almost the second they create it, it's gone. So it's very hard to study it because the half-life, it just disappears very, very quickly. All right, so we're looking at a substance that has a half-life of 20 days. We start out with 5 grams. Okay, I want to write a formula for it, and then I'll figure out when I have a certain amount left.
What, like 5?
Yep, so let's write our formula, and then we'll figure out when we have less than a gram left. So James said it's 5 times.
A half to t divided by 20.
Yep. Because this exponent has to represent the number of half-lives that have gone by, not how many days. So after 20 days, how many half-lives have happened?
Oh, it's gonna be less.
So if you plug 20 in for t, how many half-lives have happened after 20 days? Just one, because the half-life is 20 days. And your exponent would be a 1. How about after 40 days? 2. 40 divided by 20, there's your exponent of 2. So let me graph this. And they want me to see when I'm going to have less than 1 gram. Okay, that should be fine. 5 times 0.5 to the x over 20. Type in 1 for your horizontal line. And let's try zoom 6. Okay, looking at the negatives, that doesn't make sense, so don't worry about the negative. But I did not hit it within 10 days. Okay, so let's go out to 100 days. There's my substance.
Oh yeah, you'll hit it.
Decaying. Yeah. And they intersect at 46.4 days. So when will I have less than 1 gram remaining?
47.
That's when I have exactly 1 gram remaining.
47 days.
Or
less than that, or greater than that.
or greater than that.
Yeah.
Anything greater than 46.4 days, and I will have less than 1 gram. At 46.4, I have exactly 1 gram. So when will there be less than 1 gram remaining? We'll just say greater than, what was it? 46.4 days. Or you could also say after the 46th day, 46.4 day. Okay. Okay, so any questions on that? So that's exponential functions. Okay, and that's it. So we've wrapped those up, and we'll finish our last kind of function tomorrow, which is logarithms. Okay, so homework tonight on 268. Okay, it's 4 through 7. 19, 25, 27, 31. 35, 47 to 49, and 57. Okay, so again, we'll take a look at that tomorrow, and my extra help this week will be on Wednesday because of the conferences on Thursday.